China says it has now begun analysing data collected by its Chang'e 5 probe on the moon.
Long before any humans set foot beyond Earth's cradle, the moon kept half its story buried in darkness, its unseen hemisphere holding questions that stretched across generations of scientists. When China's newest lunar missions crossed that ancient divide, the discoveries they carried back did more than illuminate a hidden landscape. They quietly unsettled ideas once believed unshakable. The silent hemisphere. For as long as humans have observed the night sky, the moon has appeared deceptively familiar, presenting the same luminous face through every era of our existence. This unchanging view was not a matter of chance, but the natural consequence of tidal locking, a celestial rhythm that caused the moon's rotation to match its orbit and left its far side turned permanently away from us. While early astronomers imagined oceans, mountains, or even civilizations in that unseen expanse, they could only speculate about what lay beyond the boundary of visibility, since Earth itself blocked every attempt to observe it directly. As telescopes became more sophisticated, the desire to understand the moon's hidden hemisphere grew even stronger, especially as scientists began to suspect that the far side might hold clues to the earliest chapters of lunar formation. Yet the technological obstacles remained severe, because any spacecraft venturing over the horizon would immediately lose radio contact, stranding data in silence. For decades, this limitation created a scientific blind spot that no major space program could fully overcome. The persistence of this mystery shaped political ambitions as well, because whichever nation solved the communication barrier first would gain access to the last unexplored surface in Earth's cosmic neighborhood. This rising interest set the stage for an unexpected pioneer, engineering the first footsteps in darkness. The breakthrough arrived when Chinese engineers committed to solving the communication problem that had constrained every previous attempt to reach the moon's hidden hemisphere. Their solution involved positioning a relay satellite, Queqiao, at the Earth-Moon L2 point, a delicate gravitational perch that allowed the satellite to maintain continuous visibility with both Earth and the far side. By treating gravity itself as part of the communication infrastructure, the mission designers created a stable corridor through which signals could finally travel unobstructed. This strategic placement transformed an unreachable region into a navigable scientific frontier, opening a path no other space program had successfully achieved. With this bridge in place, the Chang'e 4 lander descended toward the South Pole Aitken Basin, a colossal scar left by an impact so ancient and violent that it excavated material from deep beneath the lunar crust. The choice of landing site reflected a clear scientific intention, since a basin created by such an extreme collision offered access to rocks that predated most of the moon's visible surface. When the lander touched down, its instruments entered an environment shaped by billions of years of unbroken isolation, untouched by Earth's heating influence, and shielded from direct observation throughout human history. As U-22 rolled down its ramp and began navigating the crater floor, it carried more than cameras and spectrometers. It carried the weight of a historic transition in lunar science. Every meter it traveled promised insights into the moon's internal structure, because the terrain beneath its wheels was shaped by forces that textbooks described but could not yet confirm. The stage was set for findings that would force researchers to reconsider long-held assumptions about lunar evolution. The discovery that redrew lunar history. When U-22 began scanning the regolith with its infrared spectrometer, the data immediately revealed minerals far different from what scientists expected to find on the surface. The rover detected olivine and low-calcium pyroxene, both of which are associated with the lunar mantle rather than the crust, suggesting that the ancient impact which carved the South Pole Aitken Basin had excavated material from remarkable depths. This confirmation allowed researchers to examine interior layers of the moon without drilling, thereby granting access to evidence that previously existed only in theoretical models or laboratory simulations. The surprise did not end with mineral composition, because subsequent analysis conducted on returned samples from the Chang'e 6 mission revealed volcanic rocks significantly younger than anticipated, Among fragments dated to roughly 4.2 billion years were basaltic samples that averaged only 2.8 billion years, which contradicted assumptions that the far side had cooled quickly and become volcanically inactive soon after its formation. These younger rocks indicated that magmatic activity persisted long after thermal models predicted solidification, introducing a complication to the prevailing narrative that the moon's smaller size should have caused its interior to cool far more rapidly than Earth's. Such findings prompted researchers to revisit long-standing theories regarding asymmetric heat distribution across the lunar hemispheres. Earth's early radiative influence should have kept the near side warmer for a longer period, which would logically lead to extended volcanism in that region rather than on the far side. The unexpected youth of the far side lava flows implied that internal heat sources, compositional differences, or mantle dynamics were far more complex than previously understood. These revelations ignited a renewed scientific interest in the moon's thermal history because each new sample challenged a structural assumption that had anchored lunar research for generations. Taken together, these discoveries demonstrated that the moon's evolutionary path was neither simple nor static, and that the far side held records of geological processes that reshaped scientific expectations. The tectonic whisper beneath the far side. As researchers continued to interpret the data streaming through the Queqiao relay, they noticed patterns that suggested the moon's internal story was even more dynamic than the mineral findings implied. Instruments aboard Chang'e 4 detected seismic signals that aligned with known categories of moonquakes. Yet several readings displayed amplitudes and timing inconsistent with surface expansion, caused solely by temperature changes at sunrise. While thermal moonquakes were expected, the strength of certain events indicated involvement from deeper layers, prompting scientists to question whether the moon's interior had cooled as completely as long-standing models proposed. The discovery that some of these vibrations originated from regions beneath the far side raised the possibility that portions of the lunar mantle retain pockets of partially molten material. This interpretation gained traction because the seismic signatures appeared too energetic to be produced by superficial processes alone, implying that internal stresses were still redistributing heat or adjusting to structural imbalances created over billions of years. If true, the moon's interior would not be a dormant sphere of solid rock, but a body experiencing slow, residual movement, shaped by ancient collisions and uneven cooling. Such an insight added a new dimension to the younger volcanic samples retrieved by Chang'e 6, because ongoing internal activity could help explain why the far side exhibited magmatic features that contradicted thermal expectations. The potential presence of residual melt suggested a prolonged and uneven cooling cycle that challenged the idea of a uniformly solidified lunar mantle. This realization motivated researchers to re-examine the moon's thermal mechanisms with greater nuance, since understanding its internal vitality had implications for resource detection, structural stability, and future habitation plans. The evolving portrait of a moon that still whispers through subtle tectonic motions set the stage for reconsidering what else might lie beneath its surface. Helium-3 and the resource frontier. The scientific revelations emerging from China's lunar missions quickly intersected with a different kind of curiosity because the far side did more than preserve geological history. It accumulated resources unavailable on Earth. When the Chang'e 5 mission returned samples from the Mons Rumker region, researchers identified a transparent, colorless mineral, later named chondrosite. Why? Although its crystal structure measured less than the width of a human hair, it carried profound implications due to its association with helium-3, a rare isotope on Earth, but abundant across the moon's exposed regolith. Helium-3 is deposited by the solar wind, which cannot penetrate Earth's magnetic field, but freely coats the lunar surface over billions of years. Scientists value this isotope because of its potential role in next-generation fusion reactors, where helium-3 could provide high-efficiency energy with minimal radioactive waste. While functional helium-3 fusion remains technologically out of reach for now, the presence of an estimated 1 million tons across the moon represents a long-term incentive that extends far beyond scientific curiosity. The far side, shielded from Earth's magnetosphere and exposed to uninterrupted solar flux, is believed to contain especially rich concentrations, making it a region of strategic significance. These resource considerations blend with the geological discoveries to reshape international priorities, because understanding where minerals originated helps determine how accessible they might be for future extraction. As nations evaluate prospects for sustained lunar operations, the far side's unique composition positions it as more than a scientific archive. It becomes a potential energy reserve for future generations. This expanding awareness of economic and scientific opportunity narrows the focus onto the growing competition to establish a lasting foothold on the moon. The race to permanence. As scientific insights accumulated, space agencies recognized that understanding the moon's hidden hemisphere was only the first step toward shaping a long-term presence beyond Earth. China's upcoming Chang'e 7 and Chang'e 8 missions reflect this transition, since both aim to investigate the polar regions where ice deposits may serve as vital resources for life support, fuel production, and construction materials. By testing in situ resource utilization technologies, these missions move beyond exploration and toward infrastructure development, signaling a shift from temporary scientific visits to the early stages of settlement planning. Meanwhile, NASA's Artemis program, intended to return humans to the lunar surface, has faced delays that pushed its schedule several years beyond initial projections. This shifting timeline creates a strategic opening, because whichever nation establishes operational systems first may influence the standards, partnerships, and logistics that shape future lunar activity. With each mission, China strengthens its technical foundation and demonstrates a methodical approach to building capabilities that support sustained occupation rather than symbolic achievements. These parallel efforts underscore an emerging reality in which scientific discovery intertwines with geopolitical ambition. The moon is no longer viewed merely as an observational outpost, but as a domain where early leadership may carry consequences lasting well into the next century. As nations push deeper into the moon's uncharted hemisphere, each discovery reshapes our understanding of how worlds form and how far human ambition can reach. Stay curious, subscribe to follow every breakthrough, and keep exploring with us as the next chapter of lunar history begins.